Welcome to the Organic Chemistry Chem 652 video office hour. We're going to go over a couple of things. One of the things I wanted to do was discuss the mechanism of the alkyne isomerization reaction. I covered that in class, but it was a challenging mechanism and I think it would be worthwhile to go over that again. I'm also going to talk a little bit about the Diels-Alder cycloaddition reaction. And I'm going to go over some problems, including a couple homework problems and other problems that are closely related to homework problems. Those will include a free radical reaction or two, reactions related to the effects of conjugation. So these are from two separate chapters, the two chapters that are covered on Quiz 1. And the problems we go over will include at least one, if not a couple different synthesis problems, and a couple of Diels-Alder cycloaddition problems. So that's what we're going to cover, and we're going to do it right in that order. So we begin with the mechanism of alkyne isomerization. And I want to remind you that this reaction is one which converts an internal alkyne, regardless of how large it is. This one's quite large, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is a 12 carbon internal alkyne, and at the end of the reaction we'll convert it to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, a 12 carbon terminal alkyne. This would be 1 dodecine. 1, 2, 3, 4, 5, 6, whereas this was 6 dodecine. And the reagents that are required to convert an internal alkyne to a terminal alkyne are, in the first step, potassium amide in liquid ammonia, and then in the second step we have to quench with H2O. So those reagents are always going to be the same. This is one representative example, but I'm not going to show you the mechanism for this one because it's just too long. We'd have to show a really long mechanism where we convert, where we essentially move the alkyne position from 6 to 5 to 4 to 3 to 2 and eventually out to 1. So that would be a very, very long mechanism. Instead, for the mechanism, we can effectively get the same information with regards to how the reaction works by starting with a simpler case like this 2-butyne. And converting it into 1-butyne. So that's going to be the mechanism that I show you. This is actually the very same mechanism I showed you in class. Let's go through it. Well, as I told you, a real key to this reaction is the fact that potassium amide is an exceptionally strong base. We have here, with our alkyne, these protons right here, these 3 hydrogen atoms, any one of which could be removed as a proton by a very strong base, that are adjacent to the alkyne function. And that's really key. Being adjacent to the alkyne function means that if I remove one of those protons, and there are the two electron arrows which would be required to show this, then I'm going to produce an anion in which the lone pair and the negative charge is on a carbon atom that's adjacent to the alkyne function. And the reason that's significant is because it means that this carbanion, a carbon anion, this carbanion does not have its lone pair and its negative charge localized on one carbon atom, but it is in fact a resonance delocalized situation. So as a resonance delocalized anion, it's going to be a little bit more stable, a little bit easier to form. So that's really a key. The other half of the picture here is that when the amide picks up the acidic proton, we generate ammonia. Now we're running this reaction in liquid ammonia, so there's plenty of ammonia around. You don't necessarily have to use the ammonia that you just created for this next step, but as long as we've drawn it, and we should draw it because this is a mechanism, let's go ahead and use that particular ammonia. And so you see what I'm going to do here is I'm simply going to regenerate amide anion, and at the same time this cumulated diene. This cumulated diene is cumulated because the two pi bonds are on adjacent carbons. So this would be a 1,2 butadiene. A 1,2 butadiene makes that kind of special. So let's review what we've done so far. It's really just a series of acid-base steps. We start out with a very strong base, amide, and we pull off a proton that's adjacent to the alkyne function. That's going to give us a carbanion, which is resonance delocalized. Here are my two resonance forms. And you can see from these two resonance forms that there's negative charge character at two different carbons, this carbon and this carbon. If I were to just simply reprotonate this carbon, I'd be right back to where I started. And in fact, that does happen. That's what the equilibrium arrow means here. We're going back and forth. But because this carbon over here also has quite a bit of negative charge character, it can be protonated by ammonia in order to generate this cumulated diene. Plus, we regenerate the amide anion. So now I'm going to take the amide anion, and I'm going to pull off this terminal proton right here, kicking the electrons onto the adjacent carbon. And once again I generate an anion, which is going to be resonance delocalized. If I take these two electrons, kick them down to form a new pi bond, I must move these two electrons, these two pi electrons, to the adjacent carbon so that I don't have a violation of the octet rule at this central carbon. That gives me a new resonance form. Which looks like this. This is starting to look a lot like the terminal alkyne. Since it was amide, which picked up this acidic proton to generate this resonance delocalized carbanion, I must have, in the same step, produced ammonia, NH3. And once again, there's lots of ammonia floating around. It is the solvent for this reaction. But I'm going to go ahead and use the one that I just created. Now the ammonia is acting as the weak acid, protonating this strong base. This carbanion would be very basic. And it gives me the terminal alkyne as product, plus we've once again regenerated that very strong amide base. Now, you might be tempted to think that's the end of the story, because after all, we started with an internal alkyne and we've now created a terminal alkyne, but it's not the end of the story. In fact, if that were the end of the story, this wouldn't be much of a story at all, because so far we just have a massive equilibrium, and these species would all be present at equilibrium. The neutral species, like the starting material, the cumulated diene, and the terminal alkyne, would probably be the three dominant species at equilibrium. but you'd have more than one species at equilibrium. It wouldn't be as nice a reaction as it turns out to be. Because it turns out that of all the alkyne or accumulated diene species that are equilibrating, there's one that's special, and it's this one right here. This terminal alkyne has a relatively acidic proton right there at the terminal alkyne function. Much more acidic than any of the other protons we've been plucking off with the strong base sodium or potassium amide. And so, because we form this terminal alkyne in the presence of this very strong base, there will most definitely be one more step. There's my 2-electron arrow where I'm picking up the acidic proton, but because this proton is so much more acidic, this last step is irreversible. So unlike the prior steps, which were all reversible, the last step is irreversible, and it generates this new anion, and we refer to this as an acetylide. So that's an acetylide anion, plus of course we produce ammonia in that step. And that's where the reaction stops. This last step is irreversible because I have a much stronger acid and still a very strong base. So the whole equilibrium eventually settles in on this acetylide anion and it just stops there. Then we come along in our second step and we add H2O. And the purpose of the H2O is to protonate the acetylide to give us a neutral terminal alkyne, which we can now isolate and use. But it's also around to quench any excess amide which is floating around, and there should be quite a bit of it. So you're not done after you form the terminal alkyne for the first time, because it's formed in the presence of a very strong base. That's going to generate the acetylide anion in an irreversible fashion. It's only after the second step, when you add water, that you've generated, once again, that terminal alkyne, but this time as a species that's going to stick around. So that's the mechanism for the alkyne isomerization reaction. Well, another thing I wanted to go over was a Diels-Alder cycloaddition. We covered this last time in class, and we're going to cover it again in the next class, but it's a good idea to go over it and talk about the Diels-Alder cycloaddition, particularly for these cases where we have our diene inside a ring. I showed you an example in class last time of a diene that was exocyclic to a ring, but here the diene is included in the ring. And the reason that's significant is that if we do a Diels-Alder cycloaddition with a dienophile, like this ethylene, the new six-membered ring we're going to form is going to involve formation of these new bonds right here. These pi electrons are going to be utilized to form this new carbon-carbon sigma bond. We're going to have to kick those two pi electrons over there in order to avoid a violation of the octet rule right there. And then these two pi electrons over here to form this second new carbon-carbon sigma bond in order to avoid a violation of the octet rule right there. The result is that we formed a new six-membered ring, which, I got a little sloppy there, but there's one of my new bonds, there's one of my new bonds, those are both sigma bonds, and there is my new pi bond. Notice that I made no attempt to get this bridge out of the way. I've just sort of stuck it right in the middle of this new molecule. It's a pretty ugly looking molecule. I'd prefer that we drew it in a different way, where we show more of the three-dimensional nature of this structure. So in other words, I'm going to put this carbon right here up top. There's my six-membered ring, the same as this six-membered ring. The pi bond remains in the same spot, but this bridge here between these bridgehead carbons is shown in a more traditional way. So what's unique about the Diels-Alder reactions that involve dienes inside of rings is that they form bicyclics, bridged bicyclics. If you remember, the way we would name a bicyclic is to count around the longest chain first, followed by the second longest chain, followed by the shortest chain, or rather than use the word chain, we really should be using the word bridge. These bridgehead carbons are held together by 3 bridges. Here's a 2-carbon bridge, here's another 2-carbon bridge, and here's a 1-carbon bridge. We would start counting around this 2-carbon bridge because it contains an alkene, whereas that one does not, so that would take precedence. Start numbering at the bridgehead carbon. 1, 2, 3, 4. Now we number around the next largest bridge, which happens to be the same size, but it's the one without the alkene. 5, 6, and finally 7 up top. So we would name this a bicyclo, and then we'll go ahead and put the lengths of the 3 bridges. Now here, the length of the bridge between the 2 bridgehead carbons is 2, and 2, and 1. 2, 2, 1. There are a total of 7 carbons, so this is going to be a heptene because it's an alkene, and we want to specify exactly where the carbon-carbon double bond is, and so we would call this bicyclo 2,2,1 hept2-ene. So that's formed through this Diels-Alder cycloaddition. Now, as we will discuss in class tomorrow, and maybe by the time you watch this video you've already heard this explanation, there are actually a couple of different products we have to be aware of. These are diastereomers, endo and exodiastereomers, that can result when we form bicyclics through Diels-Alder reactions like this. This simple example I just gave you does not have an endo and an exo isomer. There's just one product, and I've shown it. But if I were to introduce a substituent on my dienophile, so for example, let me just put a chlorine atom there. Now, when I go ahead and run my Diels-Alder cycloaddition, showing my new 6-membered ring here, I'm going to show my aeroformalism, as always. And there's my bicyclic. Notice that there's a new pi bond forming right here. These 2 carbons right here are the same 2 carbons that originated with the dienophile, so I've still got this chlorine on here. But let's not lose track of the fact that there's hydrogens on here as well, and I'm going to draw them all. So I got to figure out where to draw this chlorine. Well, there's only 2 opportunities here, or 2 options. One is that the chlorine could be up, in which case the hydrogen, which was attached to the chloroethene, is down. And then over here, there's a couple of hydrogens. I guess I don't have to draw those in. Those are just methylene hydrogens. But just as with the chlorine and the hydrogen, one of those would be up and one of those would be down. So that's one possibility. Notice that I've drawn this bridged bicyclic with the chlorine up, which means it's closer to this bridge right here, this 1-carbon bridge, but further away from this pi bond which developed during the course of the reaction. The other possibility is that you would make the diastereomer, which would have the hydrogen up and the chlorine down. And so you can see the chlorine down, it's now closer to this pi bond that developed during the course of the reaction, but further away from this 1-carbon bridge. We call the isomer in which the substituent is formed closer to the developed pi bond. That's the pi bond which was formed here. It developed during the course of this reaction. We refer to that species as endo. So this is the endo structure. And when our substituent is further away from that developing pi bond, we refer to that product as exo. So we have both an endo and an exo product in this case because we started with a dienophile that had a substituent. Let me give you another example. This is one I think is seen, if not exactly like this, awfully close to this in a homework problem. This compound right here looks exotic. It's a couple of alkenes. They're not conjugated to each other directly. A couple of alkenes that are adjacent to these carbonyl groups. It doesn't really matter which alkene reacts with our diene. This is a dienophile and that's also a dienophile. We're going to see one or the other. I'll choose the one that's closest here, reacting with our diene in a Diels-Alder cycloaddition. I'm going to draw in those dotted lines so I can keep track of the new six-membered ring that will develop. Those pi electrons will be used to create that carbon-carbon sigma bond. These pi electrons get kicked over to make a new pi bond. And these pi electrons get kicked over here to make a new carbon-carbon sigma bond. The result is that once again you have a bicyclic, and there's that developing pi bond. It's fully developed now. And here are the two carbons that were associated with my dienophile, this particular alkene. Now notice that there are a couple of hydrogens here which weren't drawn until this moment, and then there's the rest of this ring. And once again I have to decide whether the hydrogens are up or the ring is up. This is essentially a dienophile with two substituents tied together through this ring, so they're either both going to be up or both going to be down. For example, if I showed them both up, it might look something like this. So that's the rest of the six-membered ring here. These two carbons have reacted to form the new six-membered ring there. And of course we've got this bicyclic structure. And that would mean that these two hydrogens are down. Now let's look carefully. Our substituent, which is a fairly large ring substituent attached to both carbons, is not close to the developed pi bond. It's as far away from that developed pi bond as it can be. It's on the opposite side. So we would refer to this particular isomer as the exo product. But we know that we are also going to form an endo product. There's that developed pi bond. In the endo product, I'm going to have my two hydrogens up, and my ring is down. And now you can see that my substituents, which are this ring, which is this ring here, attached to both carbons of the dienophile, is down closer to the developed pi bond, and so I would refer to this as my endo product. So in those cases where you have formation of a bicyclic and a dienophile that has one or more substituents on it, you need to specify whether you're making the exo or the endo product, and in reality you need to draw both, because in most reactions, almost all, you'll get a mixture of exo and endo. For our purposes, we're not going to worry about those exceptional circumstances where you might only get one or the other. We're just always going to realize that we need to draw both an endo and an exo product, and you should be able to identify which is which in the way that I've discussed. So those are a couple of extra Diels-Alder cycloaddition problems, and I think what I'd like to do now is simply look at some homework type problems. So going back to the free radical chapter, there was a homework problem which may not have been exactly like this, but it's similar. And the question basically says, predict the products of chlorination, which means photochlorination. And then we're going to go ahead and take the exact same substrate and predict the products of photobromination. Now, hopefully you remember, photochlorination is not a terribly selective reaction, whereas photobromination is. With photochlorination, we're basically going to see a monochlorinated product, which means we've added one chlorine to the molecule, really replacing a hydrogen atom. It's not an addition, more of a substitution. We're substituting one chlorine for a hydrogen atom on this molecule, and we can do it in a variety of different ways. So hopefully you see the symmetry here. These two methyl groups are identical to each other. If I put a chlorine atom there or there, it would result in exactly the same molecule. And if that's confusing in any way, just go ahead and do it and name them, and you'll see that they have the exact same name. So my first product is going to result from a photochlorination at one of those two methyl groups, and I've chosen the one on top. But that's not the only hydrogen. Those two methyl groups are not the only unique type of hydrogen on this molecule. There's another one there, and there, and there, and there, and you're going to get monochlorination products at all of those positions. And if there's any confusion about whether or not you should be drawing all of these different monochlorination products, once again, our litmus test, so to speak, is to simply name the molecules. And if you go ahead and look at these 1, 2, 3, 4, 5 different structures and named them all, you'd see they all have different names, and so they're different molecules. What we've done is we've essentially identified all the different types of hydrogens that are on this structure: the methyl hydrogens, the methine hydrogens, two different types of methylene hydrogens, and finally a unique type of methyl hydrogen different than those methyls. Those are all different types of hydrogens on this molecule, and substituting a chlorine for any of those hydrogens results in a different structure. We refer to these as the monochlorination products because mono, one chlorine has substituted for one hydrogen. It is conceivable that if you ran a photochlorination or a photobromination, but probably more likely a photochlorination on a molecule like this, using a large excess of chlorine, and you continued to shine ultraviolet light, you could in fact get to dichlorination and trichlorination and tetrachlorination, etc. products where you're adding many more chlorines than just one. But if we confine ourselves to monochlorination products, the problem becomes simpler, and so that's what we've done here. We've confined ourselves to monochlorination products. We're looking at all the different monochlorination products. I would not expect that you could predict the percentages of these, of course. It'd be really hard to do. So we're not even going to go there. We're just going to assume that they're all made, and you should be able to draw them all. So in a predict the product problem, you'd have a whole bunch of products to draw. Now that is very different from the second reaction. Here we have a photobromination. We know that the bromine radical is much more selective than the chlorine radical, and it's going to seek out that tertiary hydrogen right there, because when it plucks off that tertiary hydrogen, it makes the most stable tertiary free radical. And at the end of the day, for the highly selective bromine radical, that makes all the difference in the world. We can predict in this case that this would be the only product, because that's the only tertiary hydrogen. All the other hydrogens are either primary or secondary. Why the difference? Much more highly selective photobromination reaction involving a much more highly selective bromine radical, and a much more reactive, higher energy, less selective chlorine radical involved here. Okay, so that's one problem. Let me look at another one. This one was also, if not exactly from the book, really close. And if you look carefully, I have here two molecules which are diastereomers of each other. This one is trans or E3-hexene. This is cis or Z3-hexene. And we're going to run the same reaction on both of them, the same reaction being a free radical hydrobromination. So here goes HBr, peroxide, and either heat or light, and I'm going to choose light. And I'm going to run the exact same reaction here. Well, we know that this free radical hydrobromination will be anti-Markovnikov, but if we look carefully at the alkenes, both of them are secondary in both cases. So what does it mean? It means it doesn't really matter where the hydrogen goes and where the bromine goes. There's no particular selectivity here, as they're both secondary. They're evenly substituted, symmetrically substituted alkenes. And if you think about it, it doesn't really matter in terms of the number of products you form because of the symmetry in the structure. Whether you add hydrogen here and a bromine there, or vice versa, you get exactly the same product. And again, if that's confusing to you, then draw them both out and you'll see that in both cases, whether you added hydrogen here and bromine there, or vice versa, you get 3 bromo hexane. Now this is a chiral compound, and so we know we're going to have to form this as a racemic mixture. And in fact, if I go up to the prior problem, there were probably some examples of chiral compounds. How about this one? Is this chiral? It is. This is a stereogenic center, so that would be made as a racemic mixture. Not this one. This one's chiral. It would have to be made as a racemic mixture. This one is chiral. Racemic mixture, but not that one. Back to this free radical hydrobromination. I just ran the reaction on the trans 3-hexene. Now let's run it on the cis 3-hexene. And what you see is that as soon as the pi bond is lost, we lose the cis and the trans stereochemistry. So in other words, we are going to get exactly the same product. It didn't really matter whether we started with the cis or the trans 3-hexene. When we run a free radical hydrobromination, we're going to get exactly the same product. What's unique about this particular case is that had we run a polar hydrobromination, so for example, no peroxide, no light, no ultraviolet light, just HBr, we would also have gotten exactly the same product. And that's because of the symmetry in the structure and the fact that there really is no Markovnikov or anti-Markovnikov nature to this particular reaction, given the fact that both of those alkene carbons are secondary. Okay, so we've looked at a couple of free radical reactions. There's one more I wanted to go over, which is related to photohalogenation. This is a problem taken out of the homework, which I really like. And I think I've changed it because the homework problem had this as a CH2Cl, so I've changed it to a CH2Br, but it is otherwise identical. And what you notice is that this carbon right here is a stereogenic center. It's bound to 4 different atoms or groups: a hydrogen, a bromomethyl, a methyl, and an ethyl. So it is stereogenic. And now the question is, what configuration are we looking at? This one's a little bit challenging, but if you look, you orient your eyeball so that you're looking straight down the carbon-hydrogen bond with the carbon in front, what you'd see is that the CH2Br followed by the ethyl followed by the methyl gives you a counterclockwise rotation, but that's with the hydrogen in front, so we have to switch that to an R. Conversely, if you oriented your eyeball looking this way so that the hydrogen is in the back, then you would go from a CH2Br to the ethyl to the methyl, and that is indeed clockwise rotation R. So this is the R configuration. And the question is, if we were to run a photobromination, and I hope you know that we would really, since it's a photobromination, be picking on this particular hydrogen because it's on a tertiary carbon. And let's just say we went ahead and we made the corresponding product. Would that be the only product? And what I've done here is I've kept the stereochemistry exactly the same. I've literally replaced the carbon-hydrogen bond with a new carbon-bromine bond in this photobromination reaction. Would that form, or would we form, it's an enantiomer. And in order to draw its enantiomer, I could just bring the bromine down, and move everything else up, almost like a Walden inversion in an SN2 reaction, but this is very different. I'm simply drawing the bromine on opposite sides of this cone to give rise to the enantiomer. Well, which is it? Would you form one only? Would you form the other only? Or would you form the two as a racemic mixture? Now, normally in these reactions we talk about forming racemic mixtures, but that's because we start with compounds that are optically inactive, achiral compounds in so many of these reactions. And we know that if you start with an achiral compound that is optically inactive, you must produce a product slate which is optically inactive as well. But in this case, we don't have that. We're starting with an optically active chiral molecule, one configuration only. So what's going to happen in this photobromination? Will we still wind up with just one configuration? Will it be the same configuration? Will it be the opposite configuration? Or will we wind up with a racemic mixture? This is a good problem because you really have to think carefully about the mechanism. Now, I'm not going to draw the entire photobromination mechanism, but let me just go ahead and indicate to you that in the photobromination reaction, in the initiation step, our bromine is going to be split into two bromine radicals by light. And this bromine radical is going to come along and do a hydrogen atom abstraction. And the reaction would look something like this. And when we talked about the structures of free radicals, we talked about them existing not necessarily as perfect trigonal planar systems in which this carbon here, the one that bears the unpaired electron, is perfectly sp2 hybridized, but rather we talked about a shallow pyramid. But that shallow pyramid can exist on either side. In other words, I could just as easily draw the shallow pyramid this way. And in fact, the structure probably almost certainly waffles back and forth between these two shallow pyramids. Now I've got to draw the electron in this p orbital somewhere. It doesn't really matter if I show the electron in the top lobe of the p orbital or the bottom lobe, and down here the same way. I've got to draw it on one side or the other. The last step of the propagation sequence is going to be to bring in another equivalent of molecular bromine and to do a halogen atom abstraction. And that could happen from either of these two species, whether I have my shallow pyramid pointed in one direction or the other, resulting in both products forming. In other words, we can do this step of the photobromination where we're actually adding the bromine atom to the free radical from the top or from the bottom. If it adds from the top, you generate this species. If it adds from the bottom, you generate the enantiomer. So we would produce a racemic mixture because we would predict that there would be an equal likelihood for both of these events to take place. And so it's going to be a 50-50 racemic mixture. 50% of this enantiomer, 50% of this enantiomer, overall an optically inactive product. This was not a full formal mechanism here. I sort of jumped into the middle. You can go back and review the photobromination if you need to. But were we drawing a mechanism out, I would also want at this stage to indicate that we're generating bromine atom in this step, and the bromine atom can cycle around and pick up another hydrogen from another molecule, and we're often running in our propagation sequence. So I hope you understand why you'd form a racemic mixture in this particular case. That's a really good question. It makes you think carefully about the mechanism of the reaction. All right, let's do a little bit of synthesis. Synthesis problems, particularly a couple right now that involve free radical reactions. This one is taken right out of the homework. What if you had to start with cyclohexane and you wanted to produce this trans 1,2-dibromo cyclohexane as a racemic mixture? How would you do it? Well, you always want to ask yourself the question, do I know any particular reaction which would convert my starting material into my product in one step? If you know that reaction, then you're done. That's the entire synthesis, one step and you're done. But as it turns out, we don't know any reaction which starts with an alkane, or in this case a cycloalkane, and produces a dibromide, a dihalide in one step. We don't know any reaction like that. If that's the answer, then my recommendation is, let's work retrosynthetically. In other words, let's go to the product and ask ourselves the question, is there a reaction I know, any reaction, which would produce this particular molecule as product? And this is where you need to know your reactions, including your old reactions from last semester. The answer is most definitely yes. We know that if we do a polar halogenation of an alkene, we get the vicinal anti-dibromide. In this case, it's a bromination, of course, because I want to put bromines in those vicinal anti-positions. So this is polar bromination. This would involve a standard organic solvent, probably something like methylene chloride. We're not going to use water here because we don't want to do halohydrin formation. We're not going to use alcohol here because we don't want to do haloether formation. We're simply going to use molecular bromine in an inert organic solvent like methylene chloride. So that's the last step of our synthesis. And now the question is, do I know any reaction which will convert this cycloalkane to this cycloalkene in one step? If the answer is yes, then I'm done. That one step plus this second step would complete the synthesis. But unfortunately, the answer is no. We don't know any reactions which convert an alkane or a cycloalkane into an alkene, or in this case a cycloalkene. But we do know how to make alkenes. We learned how to make alkenes when we studied E1 and E2 elimination reactions. The elimination reactions make alkenes. In a synthesis problem, if you have a choice between an E1 and an E2, always choose the E2. It's a faster, generally more selective reaction, higher yielding reaction. It's definitely the elimination reaction of choice in a synthesis problem. So we're going to run an E2 elimination. What would it be of? What would we require in terms of a reactant or a substrate in order to get this E2 product? Well, if you remember, we're going to need a strong base, and in fact our E2 base of choice is potassium T-butoxide, and then we're going to need a substrate which has a leaving group, and I'm going to go ahead and choose a bromine as a leaving group. And in addition to a good leaving group, we're going to need an anti-periplanar proton on an adjacent carbon. So if you remember, the E2 elimination is going to work fastest when we have an acidic proton anti-periplanar to the leaving group. That's going to be our second to last step, an E2 elimination. You would not have to draw the arrow formalism here. I'm just including that so you can hopefully remember what that E2 elimination is all about. So this is nothing more than bromocyclohexane, a cyclohexane with a single bromine atom on it. We go back to the starting compound. Do we know of any reaction which would convert our initial reactant into this bromocyclohexane? And finally, the answer is yes. We can perform a photobromination. So our synthesis is to photobrominate cyclohexane to generate bromocyclohexane, followed by an E2 elimination with potassium T-butoxide to produce cyclohexene, and finally a polar bromination to produce the trans or anti-vicinal dibromide. So that's a good problem. Let's look at another synthesis problem. There it is. So I have a methyl propane, and I want to convert it into a 1-bromo 2-methyl propane. How am I going to do that? Do I know any reaction which would take an alkane and convert it into a brominated alkane? The answer is yes, I do. In fact, we just utilized it in the previous synthesis here. A photobromination converted this cyclohexane into bromocyclohexane. So maybe I could use that. But that's not going to work, because as you can see, in this particular methyl propane structure, I have this methine hydrogen which is going to be selectively removed and replaced with bromine in a photobromination. In other words, I can add one bromine, but not to that carbon. I can only add it to that carbon in a photobromination. So although I know how to add one bromine, I don't know how to do it in this fashion with this selectivity. So that means I'm going to have to work retrosynthetically. And I'm going to ask myself, do I know any reaction which would produce this particular compound? And if you look at it, it might look a little bit like an anti-Markovnikov type of reaction, particularly if we started with this alkene. If we did a hydrobromination in an anti-Markovnikov fashion, meaning the hydrogen winds up at the more substituted and the bromine the less, starting with this alkene, we'd get that product. The anti-Markovnikov hydrobromination is going to be the free radical hydrobromination. So the last step of the synthesis is shown. Well, now the question is, can I convert this alkane into that alkene? And I think we already decided in the prior synthesis that we don't know any reactions which directly convert alkanes to alkenes, but we can produce alkenes through E2 eliminations. So once again, I'm going to choose my E2 base of choice, and I want to make sure that I choose the right substrate for this E2 elimination. This looks like a good one. Here with my potassium T-butoxide, it really doesn't matter which of these three methyl groups is attacked by the strong base. There are 9 equivalent protons there, any one of which, if it's abstracted, will produce this product in an E2 elimination. So that's my second to last step. And then we ask the question, do I know any reaction which will convert this alkane into that bromide? And the answer is yes, photobromination. So here we're going to use a photobromination, the selective photobromination, to produce this single product. followed by an E2 elimination, followed by a free radical, anti-Markovnikov hydrobromination. That's the end of our synthesis. All right, let's look at a couple more problems. Now I'm going to look at a couple of problems which come out of the chapter that deals with the effects of conjugation. Here's a diene, and I'm going to intentionally perform a polar hydrobromination reaction. And I recognize it's polar because I don't see the peroxide, I don't see the light or the heat. This is just good old HBr reacting with this diene. We have to ask ourselves, how is this thing going to react? It is most definitely going to involve formation of a carbocation. We're going to protonate one of these pi bonds to produce a carbocation. Whenever that is true, we have to think about Markovnikov's rule. So Markovnikov's rule says, in its original translation or its original statement, says that the hydrogen winds up at the less substituted carbon, and the bromine, in this case, since it's a hydrobromination, the bromine at the more substituted carbon. But then we talked about what could be termed the modern translation of Markovnikov's rule, which is going to simply state that the reaction will proceed through the most stable carbocation. And so this is where you really have to start thinking. You have to think about the substrate and all the different ways you could protonate. You could protonate at this carbon, at this carbon, at this carbon, or at that carbon. But you have to do it in such a way that you form the most stable carbocation. So what's the most stable? Clearly, tertiary is better than secondary, which is much, much better than primary or methyl, and they don't even form. But even better than tertiary are resonance delocalized carbocations. And that's really the key to this problem. If you protonate either at this carbon right here or at this carbon right here, you will generate a resonance delocalized carbocation. Both of those protonation schemes would lead to resonance delocalized carbocations. And then you have to ask yourself, are they the same? Are those two resonance delocalized carbocations of equal energy? And it turns out they're not. There will actually be selective protonation at this carbon right here.